Okay, today let us see what is a unitary function. Usually, those who are aware of quantum computing would be knowing that all the quantum operators are unitary. The operators that are defined in like the Pauli operators, X, Y, and Z, all would be unitary. And we have as well seen in some of the videos the definition for a unitary function. Now, there are a set of quantum algorithms about which again there is a video. The Deutsch algorithm, the Josa, Deutsch-Josa algorithm, Shor's and Grover's algorithm. Now, coming to Deutsch algorithm, to understand Deutsch algorithm or Deutsch is just an generalization of Deutsch algorithm. To understand this Deutsch algorithm, one need to understand the definition of a unitary function or unitary operation. Actually, instead of saying unitary function, I think it would be good if I say unitary operate. No, unitary function would be fine. Unitary function would be fine. Let's see the definition of it and how do we apply it to different functions. Unitary operation. Usually, UF is defined for Q, denoted by unitary operation is denoted by UF. It's defined for 2 qubits. Defined for 2 qubits. What exactly it is if I have to say about it in sentences, when applied, when you apply on a function, it leaves the first qubit alone and produces the exclusive OR of the second qubit. When applied, it leaves first qubit with no change, alone or no change. That's how it is defined in quantum and produces exclusive OR. XOR we say na, we know what exactly XOR is like. I use the shortcut XOR. Exclusive OR of the second qubit with the function of the and produces exclusive OR of second qubit with the function under consideration. With the function under consideration. Why I'm saying function under consideration is, again, we define a set of functions. First is of course, you can say f is a constant function. We can have constant functions. Okay. We can as well consider identity functions. Identity functions. For 0 it is 0, 1 it is 1. Constant is for 0 or 1 it is the same, the constant C, whatever we are considering. Okay, again, the bit flip function. Bit flip function. Okay, it flips 0 to 1 and 1 to 0. Okay, yeah. Let us see the mathematical way of writing it in terms of exclusive OR. UF, when applied on 2 qubits, is written as x comma y exclusive OR of fx. Okay, this is how I will write it. Now, let us see what happens when exclusive or when UF is applied to constant function or to identity function, etc. Okay. Of course, I can go with different things as well. First, I can show you how when we consider an initial state ket 0, apply Hadamard gate to ket 0, and then apply UF, how it works. Let's see. And then go to applying it to the function. Example. Let us start with ket 0. Apply Hadamard gate. Apply Hadamard gate on ket 0. All of us know the result. On ket 0 and then apply UF. Okay. So first let's see h of ket 0. What does it give me? Of course, I know what h of 0, h of ket 0 and h of ket 1 gives me. They are ket 0 plus ket 1 by root 2. H of ket 1 would be with a negative sign. Same term, similar term with a negative sign. Okay. Now if I apply UF to this, apply unitary operator UF to the resultant. The resultant gives, what happens? Let us gives UF of ket 0 plus ket 1 by root 2. Okay. So this would be something like 1 by root 2. Okay. And then of course, just a second. Hadamard gate on ket 0. Again, I'm starting with ket 0. This also should be there. Okay. So what happens? I can clearly see it is nothing but there are because to apply UF, I should have two qubits. One is this 0 and one is this 0. One is this 1 and one is this 0. Okay. So what I will have would be UF of ket 0 0 plus UF of ket 1 0. Okay. When applied, when UF is applied, let's see what happens. On the first one, there's no change on the first qubit. Let me use a different color so that you understand. There is no change in the first qubit. On the second qubit, it works with the function. Okay. As of now, I'm not deciding the function. Once I decide, I will tell you the output as well. Okay. Yeah. So 1 by root 2 is there. Apart from this, I have first qubit is not changing. The second qubit is 0 plus f of 0. Okay. Yeah. Plus 0. No, I'm sorry. This is 1. 1 comma 0 plus f of 1. Okay. You can see above. Okay. How I have defined it, or what's the definition, how I have written the definition for it, not how I have defined it. Okay. Now here let us see what happens if f is a let f of x be an identity function, be an identity function. Then what happens? What is an identity function? F of x is equal to 0 for x is equal to 0. 1 if x is equal to 1. Okay. So let's see. X is equal to 0 and x is equal to 1. I can clearly see in the above. Okay. 1 by root 2. Ket 0 comma 0 plus f of 0 is 0 only. Right. No change in the first one. Coming to the second one. 1 comma 0 plus f of 1 is 1. Right. So let's see what happens. Okay, so I'll be having 1 by root 2, 0, 0 plus. Here I'll have 1, 1. Of course, you can observe this is the Bell state that I've got. Okay, hence this is the final state. Final. This is how I will apply, guys, because I need to have two qubits, and two qubits are possible only with entanglement, or of course, whatever you call the tensor product or whatever. Okay, only with that it is possible. So accordingly, I frame out and I will do. Okay, you can ask me. Of course, regarding XOR, just see here if anyone has a doubt. Exclusive OR. Only if I have one, it is one. I mean what? If there is only one, it is one. Otherwise, for any other values, it is zero. So for both two zeros, it is zero. For two ones also, it is zero only. Okay? Yeah. So this is how I will be doing it. What exactly I have done? I have applied UF on two qubits. One qubit is the resultant from Hadamard gate, applying Hadamard gate to Ket 0. Okay, one qubit is the Hadamard gate qubit that I applied. Okay, the other one is normal initial, our initial state, Ket 0. Okay, and hence the final result is something like this. Of course, you can go with f being a bit flip function as well. If it is a bit flip function, I can write for you here, guys. Bit flip function. How will it be? F of x would be 1 for x is equal to 0. For 0, it is, I mean, for 1, it is 0. So it flips it. So what happens here? F of 0 would be 1, f of 1 would be 0. So different output is what I will get. The other Bell state probably is what I will get. Okay. Yeah. So this resultant is nothing but 1 by root 2 ket 0 0 plus ket 1 1. Okay. This is how I will apply unitary operator, unitary function. Of course, to a identity function. Okay. Thank you.